Hi everyone, how are you doing? Okay. Hello Arnab. Hello Devesh. So let's just get started. So we have started with our, the problem statement of fitting the line, right? Do you remember this? Now let's just move on the same line and let's just see that how we can fit the line formally, or I can say mathematically. Okay. So today we are going to have an optimization viewpoint to find the best fit line, which means that suppose these 3 points are given to us. Okay, in the last class we have seen that, okay, suppose 3 points are given to us and we want to fit a line such that it is something called as best, right? I mean, we need to define the mathematical way to say this as a best. So today we will be doing it. Okay, so let me just propose a solution. Suppose these are the 3 points, right? First tell me, can there be a single line that can pass through all of these 3 points? Can there be just one line that can pass through all of these 3 points? No, right? So there cannot be a single line, right? Because these are not collinear points, so there cannot be a single line. So which means there might be some line which could be, I mean, something like that, which will definitely be not passing with all of these 3 points for sure, right? For example, however, it may happen that that line doesn't pass through all these 3 points. So we are looking for the best fit line, right? Okay. So for example, if I just ask you, is this a best fit? What do you think? Just by looking at it, can you say it is a best fit? Okay. So most of you are disagreeing, right? It is just like, you can say, I can say it's a crazy, uh, crazy example. Okay. Obviously, it's not a best fit, right? But suppose if I ask you this, what about this? What about this? How about this? This may be, right. Yes, this may be, right. This may be the best fit. But what about this? Do you remember our 3 points? So this is the third one. What about this? So it was the second solution that I am proposing, and this is the third solution I am proposing. Which you think is better? So how about this? Even how about this? How about this? So basically, this is the correct answer. Okay, this is the correct answer. So we have shown you many examples, and out of that, this is the correct answer. Okay. Yes. So we can't say without doing some mathematical calculations, right? So basically, if I show you these lines, this is the one line. Okay, this second line, for example, third line. This is the final answer. So if I show you few lines, then obviously by looking at it, you can't say. So that's why we need some mathematical way to answer this question. And what is the question? The question is that how to find the best fit line, right? So there should be some mathematical way to answer the question. So today we will see that mathematical way, that how we can find the solution of this solution of this question. So what we will be doing, let's suppose these are the points which are given to us. Now what we will be doing, whatever line we are looking for, okay. So let's suppose this is the answer, or this is the one candidate answer, I can say, right? uh no, it need not to pass through origin. The origin could be anywhere else. Okay. So whatever is the candidate answer, what you will do, you will take that answer, and you will find these residuals, okay, or these errors, whatever you want to call. So you will find these errors. So for example, if you are saying this is your answer, then how far this your answer is at a given point. For example, let's suppose this is x1, x2, x3, x4, x5, right? This is suppose x5. Okay. So suppose suppose this is x5, right? Now how far this answer is from your original one. For example, if you are predicting this as by cap or by 5, okay, then let's suppose this is y5 cap, and this is y5. I mean, this is the real one, this is the predicted one, this is the predicted one, right? So what you will be doing, you will be finding the difference between by 5 cap and by 5, right? And then not just difference, you can take the square to have the mathematical convenience, which means just to make our life easy instead of mod. I mean, mod is not wrong, but you can take a square. Okay. So this is one kind of error you are computing, and then similarly you will be computing the error with respect to this, with respect to all the other points, right? Okay, so what you are actually doing, that basically you are finding the error based on this, that you are saying that okay, based on each of the points, that you are saying that if I want to find the error with respect to y 4 or x 4, then I will be taking y cap 4 and actual y 4. So what is the actual one? This is y 4 at x 4, and y cap 4 is this one. Whatever is on the line, I'm calling it y cap. Okay, then you will be finding the difference, right? So let's just see some question, and then you will get to understand this more. Okay. For example, if I just ask you, can you find the best straight line fit? It is, by the way, it is also called as least squares. Okay. So can you find the best straight line fit that is the best fit for these 3 points? Suppose the line is ax plus b. Okay. Suppose this is the line. Then what is the value of a and b? That's what they're asking. So basically, they're asking the values of a and b, right? So let's just try solving this question. How will you do it? You will say that, see, if you want to ask for A and B, then I will do one thing. I will find the error, right? I will find the total error, which is with respect to y1, with respect to y2, and with respect to y3 also. So what is the error with respect to y1? This will be, let me see what notation they are using. Okay. So this will be the real one, which is -2. So this is basically -1, -2, 0, 0, 1, 3. Okay. These are the x and y which are given to you. So it will be -2 minus ax plus b, right? Ax plus b. So instead of x, I will be writing x1, right? This is the first term. Is this okay to everyone? Or maybe if you want, you can write y1 here. What will the second term? The second term will be similar to this. It will be, instead of y1 and x1, it will be y2 and x2, right? See, you don't have to worry whether the points are collinear or points are not collinear, because if these are the collinear, then error will automatically be zero. Okay, don't worry. We are finding best A and B. If these are the collinear, then error will automatically be zero. So here, instead of y1, you will be having y2, and instead of x1, you will be having x2. Now plus, what will you do? You will say that let me just add for y3 also. Okay. So here you will be writing for y3. Right? This is the total error. Now, what you will do, you will basically substitute the values of x and y. Let's just quickly do it. And then you will find a and b. So what is the value of a? What is the value of x and y? So x1 is -1, right? So this is as good as saying y1 is -2 minus a x1. X1 is -1. So let's just do like this. So it will be plus x1, I think, minus b, right? So my ax1, sorry, plus a minus b. This is the first term, right? The second term will be, similarly, you can write both the terms. So y2 will be 0 and x2 is also 0. So if this is 0, this is 0, it will be minus b square, right? Which is as good as saying b square. Plus the third term will be y3 is 3 minus ax3. X3 is 1. So it will be just a, and then minus b, right? So minus b. So I think these are the three terms: -2a, -2 plus a minus b whole square plus b square plus like that, right? So these are the three terms. So what you can do, you can just add just like this, right? You can just add all of these three terms, and finally you can get this E. So let's suppose E is of after some computation, the final E we are getting is this. Now what is our aim? We want to find out A and B such that this error is minimum, right? So I want to find out A and B such that this error is minimum. What we can do here, we can just just differentiate it, just single differentiation with respect to A also and with respect to B also separately, right? So we have done this in the calculus. Even if you have not watched the calculus lectures, don't worry. There's simple differentiation, the partial differentiation. Okay. So just do with respect to A, just do with respect to B. Partial differentiation means that we are keeping B constant here. We are just differentiating with respect to A. It will be 4A minus 10. Here it will be 6V minus 2. If you keep it at 0, you will be getting the value of A, which is 10 by 4. Similarly, from here, you will be getting the value of B, which is 2 by 6. So it is same as 1 by 3. It is same as 5 by 2, right? So 5 by 2 and 1 by 3 is your answers. Let's just check it. 5 by 2 and 1 by 3, right? Okay. Is this okay to everyone? That what we are trying to do? So basically, we are trying to find out the values of A and B by just simple differentiation, right? And that's how it works. So by the way, this question, the as it is question without any modification, I've taken from this university. Okay. And solution is also taken from the same university. Let me know if that is okay to everyone, that how to find A and B. So what is happening here? That given these 3 points or any number of points, what you can do, you can find you can write the expression for E, and then you can just differentiate it with respect to A, with respect to B. Now tell me, instead of 3 points, if there are, let's suppose, 10 points, then then how many equations you will be having here? Let's, for example, here you have two equations for A and B, right? So instead of 10 points, if you have, let's suppose, I mean, instead of 3 points, if you have 10 points, then how many equations you will be having here? Just two, right? Because there are just two variables, A and B. So what will change? Just this E, like number of terms in E might change, and this E might, I mean, you might face a little difficulty to find E. Obviously, we have the shortcuts here, so I will tell you the shortcuts also. Okay, cool. So is this fine to everyone? That what we are trying to do? Okay. Okay. So Ajay is asking that why we can guarantee that it is, the minima, not the maxima. Yes, actually we need to double differentiate and we need to check it. But using just intuition also we can check here that suppose if there is a function like this, right? If there is a function like this, then uh, you just consider like this, that, I mean, this is a square. So you can just, consider like minus by 1, okay? Just to visualize. Is this okay? Instead of writing by 1 minus, I can write minus by 1 because it is just a square. Is this okay to everyone? So obviously, if you increase A and B, what do you think, this E will increase or decrease? If you increase A and B, I mean, basically the thing is that, I mean, it might depend on the sign of x1 or something like that. But yeah, the thing is that mostly here, it will be like that you can increase, like, let's suppose, for example, if you increase see, the B is independent, right? If you increase this B to, let's suppose, too much, okay, to infinity. Let's suppose if I want to, maximize this, then obviously it is for sure that I can increase this B on OA also to be infinity, and if it is too much, then this these term will be almost negligible. So basically the maxima is actually infinity, right? In the sense that it is a convex function, like this. It is a convex function like this. That's another story, but intuitively you can say that maxima is actually infinity, okay? Or in other words, maxima does not exist. So basically, for these kind of functions that we are looking for, only the minimum will exist. If you want to check whether the only minima exists or the maxima can also exist, you can find the double differentiation. And in calculus, we have seen that the double differentiation is called Hessian, right? So see here that E is a function of, you can say E is a function of A and B, right? Okay. So, so if you singly differentiate it, right, with respect to A and with respect to B, then, uh, then it will be like this, right? It will be like this. If you singly differentiate it. Now, since A is a function of A and B also, not just A, it is a function of A and B both. So that's why if you double differentiate it, then it will be again with respect to A, with respect to B, again with respect to A, with respect to B, right? So how many terms will be there? With respect to A, if you do it, then you will be writing like this, right? With respect to B, if you do it, then you will be writing like this. Similarly here, with respect to A, if you do it, and with respect to B, if you do it, I think the notation is this, right? So basically these are the four terms. And in the single variable, you might remember that if you want to check for minima or maxima, you double differentiate it, right? So this is the double differentiation. And do you remember, we for the minima, the double differentiation should be less than 0 or greater than 0? Tell me, right? So basically, since here we have multiple terms, so first of all, what we do, we arrange those multiple terms in a matrix, and that matrix is called Hessian matrix. Okay, we have studied that in the calculus, but since it is not required here, that's why I'm not revising it. Otherwise, it will take too much of time, because it is not required. Whatever, see, I promise you one thing, that whatever is required for the machine learning, I will give you the enough background, even if you have not watched the calculus or LA lectures. I mean, I will make sure that that your flow is not getting disturbed. Okay, so that's why, if you have not watched calculus lecture, that is fine. Whatever is needed, I will tell you. Okay, so I'm assuming that it is fine, right? At least this is fine. Okay, so here the little assumption is that you know how to differentiate. Okay, that is just a small assumptions. Obviously, I need to do, otherwise we won't be able to proceed with machine learning. So this is the small assumption. Here, since people have asked, then only I'm just telling you that you can just double differentiate it. If you double differentiate, then actually we arrange, since we have got multiple terms, so we arrange them in a matrix, right? Just like this. So we write like this. Okay, something like this. So so actually these two terms are same. So you can write like this. So we arrange all of these four terms in a matrix, and we call this a Hessian matrix. And since we just can't check, okay, for a no, we need to check whether the double differentiation is greater than 0 or not. So we just can't check with, with the matrix, that whether it is a greater than 0 or not. So we have special methods, and that special method is called positive definite, right? So PD, positive definite. So we have seen this positive definite things. These things we have seen in linear algebra. We have seen in the calculus. So I'm not repeating those things. Okay. Okay. Anyway, so is this fine to everyone? This particular thing. So don't worry whether it is a minima or not. Okay, you don't need to cross check. For the least square solution, it is always a minima, right? I mean, if you want, you can check, but it will always be the minima. Okay. So what we are doing? We are finding A and B, right? Great. So this is the correct answer. Now, for example, if these are the, let's suppose, n points, or might be 3 points, 4 points, or like that. If these are the n points that you have, then what you do, if you want to find out the best fit line, you will be having some line. Let's suppose the candidate line is x plus b, and then to measure that how good it is or how bad it is, what you need to do, you need to basically formulate. Basically, what you need to do, you will be writing this ax plus b, and let's suppose this is y. Okay, y1. So here, basically, this is the line which we are calling ax plus b, right? Now, what we need to do, we need to find out at every of this point, right? At every of this point, this is ax. For example, this could be ax2 plus b. We need to find out the difference between ax2 plus b and y2, right? Ax2 plus b and y2. So let's just be little consistent with our notation. Okay, instead of writing by, I will always be writing by cap. If it is a predicted value, I will be always writing by cap. Is this fine to everyone? Okay, so I will be always writing by cap if it is a predicted value, and if it is a real value, then I will be writing by. Okay, so I will follow this convention throughout the complete ML series. It's not just for one or two lectures. It is for the complete ML series. That let's suppose whatever our model I'm getting, okay, which is ax plus b, then the model output I will be writing as bicap. Bicap is our model output in the sense that bicap is some value that model is predicting, and by is some value that I have as a ground truth. Okay, so I have ax plus b, which is actually equal to bicap, right? It may be exactly equal to bi also. It doesn't matter in the sense that if the points are, let's suppose, collinear, it may be exactly equal to bi. Okay, and it may be little bit higher or lower than bi. So what we can do, we can arrange all of these equations. For example, ax, this is, if you arrange like this, that b coefficient is just a 1. So a coefficients are x1, x2, xn. So say, since a coefficients are x1, x2, xn, so you can arrange like this. Do you know if you multiply these two, then you will be getting the same thing, this LHS, right? So basically, how to multiply? You will be multiplying this column with this number, this column with this number. Do you remember? And then you will be getting LHS. So basically, what I'm trying to say here is that whatever LHS you have, you can write it like this, and this is actually equal to by. Then, but we want to find out. Basically, we want to find out the difference of this, which is the model prediction, and this is what we call ground truth. Okay, ground truth is something that we already have in our training data. Don't worry, I will keep those terminology clear later on, but here I'm just using it loosely. This is called ground truth. Okay. Now, this setup, this model prediction can be written as AX. And let's just assume this vector is B. Okay. Or maybe you can assume something else. But I'm just assuming B without loss of generality. So basically, this B and this B is different. If it is confusing, then you can assume this to be P and Q, or maybe MX plus C, something like this. Okay. Suppose this is, I'm just telling you, suppose this is M and C are the parameter. So basically this A will be like this, x1 to xn, and then all the ones, and then this x will be M and C, right? Minus b. B is your ground truth basically. Okay, y1 to yn. V is the given vector that we want to uh, basically this is the ground truth that we want to achieve. Is this fine? So basically we are finding the difference between the model prediction. Let me just not have that much clumsy slide. So I hope this is fine. Don't worry about the notation. It will be clear later on. Basically, we are finding the difference between model prediction and the ground truth, right? What is the model prediction? Ax1 plus b, or like that. So we can completely write this as a vector form, which is ax, right? This is our model prediction. This is our ground truth. Okay. Now we want the difference to be very less, right? I mean, we actually want something like this. See here, what we want. This is our model prediction. This is our ground truth. We want to sum all of this, right? Sum all of these errors. Now just imagine like this. Let's suppose you are having, let's suppose, some vector v, okay, which is suppose v1, v2, v3. And if I say just consider some scalar. Okay, just consider which is, let's suppose, v1 square, small v1 square, v2 square plus v3 square, right? Suppose this is the scalar that we have. And if I just ask you that if v is this and this is some scalar, how you can rewrite this scalar in terms of the vector? Can you not write like this? I mean, this is v1, v2, v3. This is v1, v2, v3, right? So actually, you can write v transpose v. Is this okay to everyone? I mean, this kind of scalar, which is actually v1 square, the coefficients square, or the dimension, or each of the dimension you're taking and then squaring, right? You can write this kind of scalar like v transpose v. Or in other words, uh, if v transpose v is given to you, then you can write as v1 square plus v2 square plus v3 square. Okay. So this thing should be comfortable to every one of you. Is this okay to everyone? Now, okay. So now this is our model prediction, right? This is our model prediction. And this is our ground truth. So what we want to take their difference and put the square. Now, what you can say that, okay, let's just do one thing. You can say that if I consider vector, let's suppose ax minus y. Okay, so instead of b, I'm just considering y because you might get confused with the b. Okay, let's suppose ax minus y, right? So this is basically ax minus y. Ax minus y is actually having these as entries. Okay, for example, ax minus y will be having the first entry as ax plus 1 plus b minus y1, ax 2 plus b minus y2, and like that, right? Now, if I ask you that if I'm summing up all of this, if ax minus y is this, if I'm summing up all of this, then can I not say this is same as, or maybe ax minus y or ax minus b, whatever you want to consider. Let me just write y. Can you say that this is ax, since I'm summing all of this, okay, this is the summation of all of this. So this is a scalar, this is also the scalar. Okay, both are scalar. This is also a scalar number. Can I say that ax minus y transpose into x minus y? Because it is same as v transpose v. Okay. So this particular quantity can be given as ax minus y transpose into ax minus y. Is this okay to everyone? Okay. So what we ultimately want to minimize this quantity, right? We ultimately want to minimize this quantity. Now, what is this A? A is your, you can say, A is your data. Okay. This is your data, which is x1, x2, xn, but you also have 1 1 1. Okay, I mean, you just have 1 1 ones. Okay, here, so this is data augmented with ones. Okay, augmented with one more vector, which is just 1. So ultimately this is your data. What is the x? X is something that you're looking for, right? X is something that we're looking for. So if you're looking for something, we call it parameter. Okay, parameter means that we want to find out something. Okay, so this is your data, which is A, and then you whatever the parameters you have, you put them in a vector. Let's suppose A and B are the parameters. You put them in a vector, and data augmented with the ones. Okay, augmented with ones. Now minus y, and what is y here? Y is a ground truth. Okay, it is a ground truth. So you have this particular scalar quantity, and you want to minimize this particular scalar quantity with respect to what thing? Can you tell me? With respect to actually A and B, right? A and B. A and B are within X. A and B are within X actually. This is X, right? Which is A and B. So you want to minimize this with respect to X. Is this understood? So let me just repeat that what we are doing. See, I'm just writing that in the matrix format. That's all. Okay. I'm not doing anything else. So I want to minimize this ax1 plus b minus y1 whole square plus ax2 प्लस बी. या टू बी ऑनेस्ट अगर आप इतना नहीं समझ पा रहे हो ना, तो दैट्स अ प्रॉब्लम. मतलब समटाइम्स आई फील दैट यू पीपल इंटेंशनली डोंट वांट टू अंडरस्टैंड. मतलब if you are not able to understand this particular, basics, then machine learning is going to be very tough. So just push yourself. I'm not trying to demotivate you or something, but I'm just saying that you need to push yourself. Okay, you need to push your limits, you need to push your level. It's machine learning, that's going to be tough. I already told you. Okay, so that's going to be mathematically challenged. And if you have opted for already you opted for gate da, then be ready to get mathematically challenged. So you should be pushing yourself. Obviously I will be pushing myself also to explain the things clearly, but you should also be pushing yourself. ओके, इतना टफ नहीं है जितना आप लोग वो सोच सोच के बना देते हो. लाइक समटाइम्स व्हाट आई फील दैट यू लाइक सम ऑफ, आई एम नॉट सेइंग ऑल ऑफ यू, बट सम ऑफ यू इंटेंशनली प्रिटेंड दैट नहीं, लाइक दैट यू आर नॉट गेटिंग. मतलब until and unless that is spoon feeding, and until that point you will say that no, no, not getting anything. So do you agree with me? Okay, I may be wrong, but based on the years of experience, I'm just telling you. Do you agree with this? That you just wait for the spoon feeding? How many of you agree or disagree? You can just tell me honestly, or do you push yourself? You can just tell me whether you agree or disagree. Okay, I mean that's completely fine. Okay, so Pankaj is saying that he always push. That's really great. I'm really happy to hear this. Okay, so Tejas is saying when ANN comes. What is ANN, Tejas? Okay, Sirias is saying that he is also pushing. Okay, great. So basically we want to minimize this. Okay, I'm really happy to see that all of you are saying that you are actually pushing yourself. That's really great. So we want to minimize this. Is this fine to everyone? Is this fine to everyone? Okay, so we want to minimize the total sum, right? It is just that we have to go to the matrix notation, otherwise the things will be very much clumsy. So we have to go to the matrix notation. So we want to minimize the sum of this. Okay. Now, if you want to minimize this, then I'm just saying that let's just go to the matrix notation. Okay, that's the only thing I'm saying. So let's just see how we can go to the matrix notation. Okay. Now let's just assume a case that there is a vector which is v. Okay. So, so let's just assume a case there is a vector which is v. Augmented matlab, like, okay, I will come to that point. Let's just go step by step. Okay, there is a vector which is v. Suppose this vector is having v1, v2, v3 as components, and I I also ask you to consider one scalar quantity which is v1 square plus v2 square plus v3 square. If I just ask you that, can you relate this vector and scalar? I mean, can you rewrite this scalar? Then you will say that, okay, one of the way to rewrite this scalar in the terms of the vector will be like this. Okay, this is v1, v2, v3. This is v1, v2, v3. Which means if you actually want to rewrite the scalar, then you can write like this. Do you agree with this? That this scalar, which is v1 square plus v2 square plus v3 square, is same as v transpose v, right? Okay, great. Now, now you know that if some squared summation is given for you, then you can write that thing as a dot product, right? Dot product of v transpose, I mean dot product of v with v itself. Okay, you can write the squared summation of squared and the scalar as a dot product. So I just want to write this scalar. Is this a scalar or vector? The whole thing, tell me. The whole thing is a scalar or vector? This whole thing is also a scalar, right? I just want to write this scalar in terms of vector. Okay, because I have to go to the vector notation, otherwise it will be intractable. Intractable means you want to be able to manage the notations and all. So we have to go to the vector notations, right? That's the only reason. See, if we could have managed just like this, then there was a no need to go to the vector notation. But obviously, if the number of number of equations increases, and also the number of parameters. So, for example, instead of just, let's suppose, one x and y, there could be multiple features. For example, currently there is just x and y, right? Relationship between x and y. For example, I have given you the example of temperature and ice cream sold, right? Temperature and ice cream sold. I've given you this example. But do you think that there can be in future? There can be someone who will say that, okay, the ice cream sold does not only depend on the temperature, it also depend on, for example, something else. For example, humidity. Do you think that someone else can come in future and can say that, okay, actually y is a function of two things, right? Do you agree? Not just temperature, it is also, I mean, the ice cream sold not just depend on the temperature, it also depend on the humidity. And maybe in future someone comes and will say, see, it does not only depend on these two, it actually depend on the direction of the wind. Okay, or maybe wind speed. If this is too much of the wind, then people might not like to buy the ice creams, right? Because it may float around, it may just go in the air. Okay, so someone in future may come and they will say that, okay, it actually depends on three things, not just on the temperature, it depends on the humidity, it also depends on the wind speed, right? So basically these are called features, right, on which y is dependent on. So these number of these columns may keep on increasing, right? So, if I write like this, to be honest, it won't be manageable. So that's why we need to move to some vector notation, some matrix notation, such that everything can be, very like packed notation, and it can be very much manageable. So that is the only reason the scalar, this, like, we are starting with this motivated example. I mean, the simple toy example, and the motivation is that we want to move towards the vector notation or the matrix notation. Okay, slowly we will be doing it. So basically, here here I'm saying that this scalar, whatever is given to us, actually have to be converted into the matrix notation, right? Okay, so just tell me that how we can do it. Now you know that if you have v1 square plus v2 square plus v3 square, then we can write it as v transpose v, where v is v1 v2 v3. So can I define a vector? Okay, I will name it little later, but can I define a vector like this, which is actually ax1 plus b minus y1, ax2 plus b minus y2, and so on. Or maybe let's just have three numbers, plus b minus y3, right? I don't want to call this vector anything for now. Let's just call it an v. Okay, anything. Okay, so basically, if this is v, then what is this? Isn't it v transpose v? Tell me. So if this is v, then this is v transpose v, right? Do you all agree with this? Okay. Okay, great. So now what we can do, instead of, I mean, what people have done, instead of saying this is a v, people have said, like, okay, instead of calling this a v, let's just call it as uh, ax minus y, where, okay, where a is like this. So okay, I can go to the next page maybe for now. Okay, so here a is something like this. So basically ax must be this ax1 plus b or like that, right? So a is something like the coefficients are a coefficients are x1, x2, x3. This is 1, 1, 1, right? And then this is ab. Is this fine to everyone? Then this will be a vector of a into x1 plus b, a into x2 plus b, a into x3 plus b. Okay. Is this fine? If a is this and x is this, okay, then ax will be this. Okay. And then y, let's just assume y to be by 1, by 2, by 3. Okay. So basically what I'm saying that this vector is ax minus y, where a is the data like this, x is just your coefficients that you are interested to find out. Okay. This is our parameters or coefficients that we want to get a and b, right? We want to find a and b. And y is what? Y is our ground truth. Okay. Y is our ground truth. Is this fine? So basically here I can write this whole thing as ax minus y. A is our data. Okay. A is our data. X1, x2, x3. There is one more 1, 1, 1 I need to keep, just because I have a coefficient which is not a multiple of any data. Okay. I mean, this is actually, this coefficient is also called something called as bias. We will talk about the bias later on. I mean, if it is not dependent on, I mean, not a multiple of the data, it is called bias. But anyway, like this is a vector which I'm interested in, a and b, right? I want to find a and b. Y is our ground truth, which is by 1, by 2, by 3. Okay. So I can say that this particular scalar is V transpose V, right? This particular scalar is V transpose V. So what is V transpose V here? V is actually your AX minus Y. So this particular scalar is nothing but AX minus Y transpose into AX minus Y, right? This is our scalar that we are interested in, which is error. Okay. This is a scalar or error that we want to minimize, or you can call it squared error. We want to minimize this such that we want to minimize this. No, y is not predicted value. Predicted is always ax. See, predicted is this. Okay, this is the predicted. I have not used y cap. If I'm using y cap, then only you consider predicted. Okay, y is the actual ground truth. Predicted is this much. This is the ground truth that I have. I'm taking the difference between both of them. Okay. So what I'm doing here, I'm writing the predicted one and the actual one, and I'm just writing. It is the only thing I'm doing. Just writing this predicted one like this, a into x. Okay. I'm writing the predicted one like this, and the actual one is anyway y. Okay. So we are interested in this a and b. So I'm just writing this ax1 plus b just like this. Okay. So basically, we want to minimize this, right? Ax minus y transpose into ax minus y. We want to minimize this. Is this fine to everyone? Right? So this is actually also called as, I mean, you can also write this as the length of ax minus y whole square. Okay. Or this is also called as norm. Yes. This is called L2 norm. Anyway, the term is not much important. Since you're not comfortable with this B, that's fine. I'm writing by everywhere. Okay. That's perfectly fine. Not an issue. So what is y? Y is our ground truth. What is ax? A is our data, right? X is our parameters. This is the data that we have, and this is the parameters. Okay. Suppose in future, if they say, okay, let's suppose there's a question. They say that suppose your data is like this. Okay. I mean, they say that you have, you know, um, two features. For example, here you have this is, let's suppose, capital. Okay, the notations are like this. I will tell you the notations. This is the y. Uh, this is the first feature in the sense that y is dependent on x1 and x2 both. Okay, this is the first feature which I'm calling as capital X1. This second feature I'm calling it x2. Okay, capital X2. Now, there could be some values. For example, this is 3, this is 5. They can give you anything. Okay. For example, 20. This is, let's suppose, 2. This is 6. This is 23. This is 5. This is 9. This is 30, like this. Okay. Suppose they give you something like this. Okay. Can you tell me what will be your y predicted y cap? What will the y cap? Your y cap will be, if you are assuming that this follows a linear relationship, your y cap will be something like this, right? So basically, maybe you can have A1, A2, A0, C1, C2, C3, C1 X1 plus C2 X2 plus C3, right? This will be your y cap actually. And your real y is this. Is this y cap a vector or a scalar? Currently, I've written as a vector directly. I mean, instead of writing that as separate, I'm writing as a vector. Okay, it's a vector directly. Now, what is the mean? Sorry, no, I'm not using the term mean. What is the squared error? Squared error is y minus y cap norm square, or maybe if you want, you can write like this. Is this fine to everyone? Let me know. Here, here, in the y cap, your parameters are hidden, isn't it? In this y cap, your parameters are hidden. So you need to minimize this error with respect to what? With respect to what? C1, C2, and C3, right? Inside this y cap, your parameters are hidden. If you want, you can write this bicap also as a different format, which will be, suppose you are writing like this, which will be a, like for example, this is your first column is x1, the whole column I'm saying x1, the next column is x2. Let's suppose this column is just one. Okay, I mean, only one is there in this column, and all the ones are there in this column. Okay, just a second, let me just tell you that what I'm trying to say. See, here, if you want, you can further expand this y cap as like this. Just x1, just x2. This is actually one. This is C1, C2, C3. Is this fine to everyone? C1 into the first column plus C2 into the second column plus C3 into 1. The third column is, it is 1. So it will be your y cap. Okay. Now, further, if you want, you can call this quantity as A. You can call whatever you want to call it. I mean, we need to actually differentiate with respect to this vector. If you're comfortable with calling it x, actually ax equal to b is a standard notation, in at least in linear algebra. In machine learning, we generally call it w. Okay. Basically, machine learning mein, तो generally a whole matrix is called x or x transpose or whatever. Basically, we call it w weights. ठीक है, but that's fine. मतलब if you want you can call it a, this is x if you want to. Okay, but I hope this is let's not get confused here, but I hope this is okay to everyone, that what we are doing, we are finding the predicted value. This is the predicted value and actual value, and the squared error is this, and we want to find out the minimum of this squared error with respect to the parameters which are always and always hidden in predictor or ground truth. Tell me, the parameters are always hidden in predicted, right? Hidden in predicted value. Hidden in the sense that if you look at this value more closely, you will find, oh, this is actually nothing but C1, C2, C3. I mean, it is a composition somehow which is making this y cap. I mean, the coefficients C1, C2, C3 are somehow making this y cap, right? So the ultimate thing is that, I mean, notation whatever you want you can use, but the ultimate thing is that we have our predicted value. So here we have our predicted value, which is y cap. We have our real value, which is y. We want to find out, we want to find out the squared summation of all of this predicted and the real. So one of the way to write it is like this, right? So we want to minimize this. This quantity is also called as squared error. Okay. This quantity is also called as square error. So we want to minimize this. Is this okay to everyone? See, we have started with the toy example where we wanted to minimize using this a and b, but we found out that it is better to write all of this in the vector or the matrix format, right? So we have actually solved one question where we have found out a and b, but now what we will be doing, we will be writing all of this in the vector or the matrix format, and then we will be solving for your a and b, or whatever you like to call it, c1, c2, c3, p, q, r, whatever the coefficients you like to call. We will be actually finding the minimum value of this, and using that we will be finding the coefficients, right? So this is our agenda. Now this y cap, if you want, you can further write it as a into x. Uh, okay, I mean these terms might be a little confusing, but here this x is the coefficients. Okay, so which means here it will be x1. This is x2. For example, let's suppose this is 1, and this will be your c1, c2, c3. Right? Okay. So basically, you have the predicted one, you have the real one. Now just to if you want then just to match with the literature, you can say this as ax, you can say this is a b. I mean, you ultimately want ax to be b, but if it is not exactly b, then there will be the difference. Okay, so in the literature, basically they call this as ax. At as per the linear algebra or optimization, in the machine learning, we have not fully moved to the machine learning, which means that it is a machine learning only. But when we fully say that, okay, now we have started machine learning, there we will be using the exact same thing, but the notation I will be using something like as w transpose x or something like that, right? So we use weight and bias, these kind of terminology in machine learning, but to get started, I'm just starting with the linear algebra. So basically, people call this as AX. Basically, it is a matrix multiplied by your coefficients, right? And then this is your ground truth. People are calling it as B. So it's fine if you don't want to call it like AX and B. So basically, this bicap is a matrix and multiplied by the coefficient, and Y is a vector. Okay, y cap is also a vector. Obviously, then only you can find the difference. Both are the vectors, but this vector can be rewritten like this, where this x is of our interest. See, why we are rewriting like this? Because I want to look at whatever is of our interest, right? So this x is of our interest, that's why I'm writing like this. Otherwise I could have not write like this. Okay. So this y cap is your predicted one, which is actually like this: ax1 plus b, like this, ax2 plus b. These are your predicted ones. These predicted ones can be written as a matrix into a vector. Okay, because this is a summation. Okay, so basically what you can do, you can take this coefficients into the vector a and b, and this is like x1, x2. The coefficients are a, coefficients are of b. Okay, so basically this bicap can be written as matrix into a vector. This bicap is a matrix, or bicap is a vector, or bicap is a scalar? What do you think? This bicap is a, here this bicap is a vector. Yes, great. So this bicap is a vector only, right? This is a vector. I'm just saying this vector can be rewritten as matrix and a vector. Okay, a multiplication of a matrix and a vector. Why I am rewriting it? Because I'm more interested in this coefficient, right? So I want to look at this coefficient x because I want to minimize with respect to x. So you can say that ultimately, okay, don't worry about the notation, but ultimately we want to minimize this particular quantity, right? Ax minus b whole transpose into ax minus b. Okay, I mean some of this form. So if you are not very, you are saying the x and x, you are getting confused. So basically it is some coefficient vector. Okay, that's all. This b is your ground truth, or I mean, don't worry about the machine learning, that whether it's a ground truth or not. But yeah, so this b is, I think I mixed it up. Like I should not have used the terms like ground truth and all. So b is something which you wanted to actually compute, which means that whatever, for example, let's suppose this is x1, x2, right? So they will give you some x1, x2, and then finally you want to get this b. How to get this b? uh, that for that you need to use some coefficients. And what are those coefficients? Those coefficients are actually this, here, right? So we want to find out the minima of this with respect to x. Is this okay to everyone? So we want to find out the minimum of this quantity with respect to x. So we want to differentiate. Let's just call it L, which is generally used for the loss function. Okay, loss with respect to x, right? For example, okay, let's just quickly have one example. Let's suppose, you have something like this. Okay, suppose you have multiple, okay, many examples. For example, you have many data points, and here this is 2 3 5 9 4 0 minus 1 2 0 minus 3 7 11 1 4 3 9. And then this is your y. Suppose your y could be anything. Okay, suppose this is your y. So basically this y, let's suppose, depends on many of this. Okay, many of these features. And if I just ask you to tell me that what are your a, what is your a, what is your x, what is your y cap, what is your y, like this, using this example, then what will you say? Is this your a? Tell me. Is this your a? We have missed something here. Can anyone tell me what we have missed? Yes, actually, we also need to write once, because there will be a term which is without the multiplication of any feature, right? Okay. And then what is your x? Maybe you can write it as C1, C2, C3, C4, C5, C6, right? 1, 2, 3, 4, 5. So C1, C2, C3, C4, C5, and C6, right? Where, for example, 2 into C1 plus 4 into C2 plus 0 into C3 plus 1 into C4 plus minus 1 into C5 plus C6 is equal to 1. I mean, all of this plus C6 equal to 1, right? So your X is this. What is your by or what is your B? Your B is this, right? I mean, as per the notation, it will be 1, 0, minus 3, 4. Okay. What we are interested in? We are interested in to find out the coefficient X. Understood? We want to find out this X, or in other words, C1, C2 to C6. Okay. All of this we want to find out, right? All of this, C1 to C6, all of this we want to find out. So I'm just writing this, the whole thing. Okay. I'm just writing this whole thing as a matrix notation so that later it will be easy for me. So I want to minimize with respect to X, or in other words, with respect to C1 to C6, or as a vector, I can say with respect to X, AX minus B whole transpose into X minus B, right? I want to find the minimum of this quantity with respect to X. Okay. B is nothing but by. Okay, B is nothing but y. So basically, I want to get this B, but obviously using A, I may not get it. I mean, maybe the linear combination of all of this may not be just B. So there might be some error, right? I mean, this AX is a linear combination of columns of A. B is something which is given to us. Our aim is to get as close as to B. Okay, we want to find out this X such that AX is as close as possible to B, right? So I can say something like this, that we want to find out as close as possible to B. Understood? Okay. So can you differentiate this? Can you differentiate AX minus B transpose into X minus B? Let's just quickly see how to differentiate. Okay. So it will be a quick detour to multivariate calculus. Okay. Just a 15 minutes detour. I'm keeping it, 10 to 15 minutes just to make sure that everyone is on the same track. Although we have discussed already, I mean, in the calculus lectures, I have just, copy pasted those slides here, but it will be worth it. Okay. So let's just quickly see. So basically, first tell me what we want to do. We want to find out the minimum of this, right? So this is our aim, is to find the minimum of this. First tell me, this whole quantity is scalar or a vector? This whole quantity, this is scalar, right? Okay. So this quantity is a scalar quantity. Now I want to differentiate this quantity, right? So we want to differentiate. How many of you have not seen calculus lectures? With respect to, we want to differentiate this scalar. Basically, you can say scalar. Okay, not an issue. With respect to X. Now, interestingly, this X, if you notice, this X is a scalar or vector. This X is a vector here, right? So this X is a vector. So you can say we want to differentiate with respect to X, which is a vector, right? So it is a kind of differentiation of scalar with respect to vector. I mean, it is a kind of differentiation of L, or what we are calling it. Okay, whatever you want to call it, L of X with respect to vector X, right? This is this kind of differentiation. Tell me, have you done this kind of differentiation? Scalar with respect to scalar? Okay, just a single variate. Okay, here x is scalar. So we have done this, right? It will be 2x. Okay. So scalar with respect to scalar, we have done this, but scalar with respect to vector, we are actually seeing very first time, right? So let's just see quickly. So basically here, this scalar, like I mean this, if you want to find out the differentiation with differentiation of f with respect to, let's suppose, x, then this f can be scalar, can be vector, or even it can be matrix. Similarly, x also can be scalar, vector, or matrix. So there are actually, you can say, 9 combinations. For example, this y. Okay, so here, let's suppose this is y. Okay, y can be scalar. This can be scalar. This can be vector. This can be matrix. Right. This is x. X can be scalar, X can be vector, X can be matrix. So there are like every possible combination is there, right? So let's just quickly see that how to find out the differentiation of one another, of one with respect to another. For example, this is, I think, very easy. Scalar with respect to scalar, this is 2x. This is very easy, right? Now, what about scalar with respect to vector? Let's suppose there's a scalar y. Okay. This y may be some scalar, which is, suppose, x transpose x. Is this a scalar or vector? If x is a vector, column vector, then y is a scalar or vector. Okay. Y is a scalar, right? So y may be some scalar, maybe x transpose x. And let's suppose we are interested in finding out. Just a second. Finding out the differentiation of this x transpose x, or maybe the differentiation of y with respect to x. Okay. Where where this, okay, you may use this d notation, or you may use this delta notation. Doesn't matter much. Okay, you can use any of this notation. Okay, see, in the calculus the notations are little confusing, so you can use any notation until and unless we are only interested in the partial notation, then only you should be using delta notation. Okay, here the delta and d both will be same here in our case. Anyway, let's not worry about it. You can watch calculus lectures for that. So this is kind of differentiation that we are interested in, right? Where x is a vector. Now, how to differentiate this? What we will be doing, we will be basically, since x is a vector, we will be differentiating with respect to each of the element of the x. For example, if x is a vector, which is like this, right? Then we will be differentiating this y with respect to each of this x. For example, if this is x, then we will be differentiating this y. Okay, y is a scalar here. Okay, you don't have y1, you don't have y2. It is just one number, y. Okay, for x you have x1, you have x2, like this. So this is a scalar, this is a vector. So you will be differentiating this y with respect to scalar, I mean with respect to vector. So you need to differentiate with respect to x1, x2, and x, and so on. Is this okay to everyone? Okay. So basically, if we are if we are doing it, see, if you are doing it, then you can write the result as a row vector, or you can write the result as a column vector. It is up to you. So for example, here I'm writing the result as a row vector or column vector. Tell me. I'm writing currently as a row vector. But if you want, you can write it as a column vector also, which means you can say if y is a scalar, x is a vector, then finally this can be, okay, the scalar with respect to the first component of the vector, the scalar with respect to the second component of the vector, and so on. Okay, so this is your choice. Either this or this. This is your choice. You can write as a row vector, as a column vector. Okay. Okay, ice cream has been fallen. That is that is because of row vector. Okay, column vectors always. That's why we use column vector more, because they are always, very nice. They doesn't let our ice cream spill off. At least they save our ice creams. Okay, so is this fine to everyone that this is a choice, right? Now, there is a term called gradient. Actually, this term, which is a scalar with respect to vector, okay, this particular thing is also called gradient. I mean, you call this is a gradient. Okay. So I've taken this from Stanford, as you can see here, that a gradient is something where you have a function which is a scalar function. I mean, ultimately it takes a vector, that's fine. For example, this fx. Okay, don't worry about this notation. By the way, this fx, let's suppose I write like this. So this is taking x vector as an input, but ultimately this is a scalar. Okay, this is scalar. So if you have any scalar function and if you differentiate with respect to vector, then as I told you, you can write it as a column vector or as a row vector, but this thing is called gradient. Okay. So for example, this slide I have taken from Stanford from some of the course. Similarly, you can write the gradient as a row vector also. The same this slide also I have taken from Stanford. Okay. So you can see the both of the slides are from Stanford. In one of the course they have used this gradient as a column vector. In one of the course they have used the gradient as a row vector. Is this fine to everyone? Okay. So both of the slides are from Stanford only. So in one of the place they are using as a column vector, one of the place they are using as a row vector. Actually, this is called as layout. Okay. So there are two possible layout options. For example, if let's suppose if x is a vector, okay. So if x is a vector, then what you can do, you can write, if this is a scalar and this is a vector. So you can write this as a row vector also. The ultimately y is just a scalar, so y only. Okay. You can write this as a column also. Okay. You can write this as anything. That is up to you. If y is a vector, then obviously for that you will be having y1, y2, y3, right? If y is a vector, x is a scalar, then just x. Okay. If y is a vector and x is a scalar, then just x, but y1, y2, y3, yn. You will be having like this, right? So if you're writing, interestingly, if you're writing this as a, I mean, it is not of much use to be honest. But yeah, if you're writing a scalar with respect to vector as a row vector, then a vector with respect to scalar is actually a column vector. Actually, this, मतलब तुम्हें ऐसे लिखना है doesn't matter. But what I'm saying that these are something specific layout. Okay, numerator layout says that it will be numerator. What is the numerator dimension? This is just one cross one, or you can say just if you don't take the initial one, it is just or the last one, it is just one. What is this? This is I mean nth n dimension. It is in Rn. It is just one. So numerator layout says the final answer will be 1 cross n. Okay, this is the numerator. I mean numerator layout first and the denominator layout first, the second. Okay, numerator layout says that okay, the final answer will be 1 cross n. For example, what is this? This is in Rn. This is in R1. So it will be n cross 1. This is called numerator layout. Denominator layout, on the other hand, says that, okay, this is 1. This is x is bold face means I'm taking as a vector. Okay. If I'm doing bold face, then it is actually a vector. So this is n. So it will be actually denominator layout first, n cross 1. Similarly, if this is n, this is 1. Then using the denominator layout, what it will be? 1 cross n, right? Anyway, we are not, I think we are not using the denominator layout. Okay. So here we will be using the numerator layout, right? We are not using this one. You can use anything, just for the sake of consistency. I'm not using this one. Okay. Actually, it won't matter. मैं इतना मतलब you don't have to know that much. I'm just saying that, okay. I mean, there are like, you can write it as a row vector, write it as a column vector, write it as a row vector, doesn't matter. Okay. Ultimately, basically, you are just following one of the layout. Which one you are following doesn't, you don't actually need to know that which one you are following. Okay. So in this lecture, we are following numerator layout. And where all the several digits are actually, if you follow denominator layout, then it is just a transpose. Okay. In most of the cases, it's just a transpose of this, right? Transpose of this. These are just transpose of each other. Okay. Let's just do this question very quickly. Suppose you have this x transpose b. Tell me this is a scalar or vector. If x and b are these vectors, this particular number, this is a scalar, right? A scalar, and you want to differentiate this with respect to x. Can you do it? Okay, let's just try to do it. Okay, so a scalar, which is 1 with respect to x is n. So 1 cross n. So I will be actually writing it as a row vector, right? Okay. So basically, let's suppose this is y. Okay. Suppose this is y, which is equal to x transpose b. Now, this del y upon del x will be, since y is just a scalar, you don't have to write y1, y2. You can just write x1, x2 like this. Right? You can just write like this. Then y, if you notice this y is nothing but, which is x transpose b. If you do it, it will be actually b1 x1 plus b2 x2 plus dot 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 b and xn, right? Can you tell me, if you differentiate this y with respect to x1, what you will be getting? If you differentiate this with respect to x1, b1, b2, b3, or summation of all of this, what you will be getting? This just this, the first number. The first number will be just b1. Is this okay to everyone? If you differentiate partial differentiation with respect to x1, it will be just b1, right? Similarly, it will be just b2, right? Partial differentiation of this with respect to just x2 will be b2. Partial differentiation of this with respect to xn will be bn. If b is this, then what is this number? This particular vector? This will be b transpose. Is this fine to everyone? Okay. So I'm asking to all of you guys who have not watched the calculus lecture, is this differentiation okay to you? Okay. Is this differentiation okay? So what you need to do, you just need to write the separate components and that's all. Let's just quickly do one or two more example and then we will just come back to our original problem statement. Okay. Let's suppose this is x transpose x. And if you want to differentiate with respect to x, then what is the answer that you will be getting? So since it is x transpose x, so you will be doing something like this, okay, which is actually equal to the, let's suppose this is y or whatever you want to call it. Let's just call it y. Okay, suppose for now I'm just taking two components, you can take more. Okay, so it will be partial differentiation of y with respect to x1, partial differentiation y with respect to x2, right? So with respect to x1, I think you will be getting 2x1. Here you will be getting 2x2, which means it is 2 into x transpose. Yes, great. Right? 2x transpose. This is what you will be getting. So x transpose x means 2x transpose. That's what you're getting, right? Okay. Now let's just quickly see that if you want to differentiate a vector with respect to a scalar, I mean the other way around, right? If it is a vector with respect to a scalar, then it will be like this. Is this fine? Since y is a vector, that's why y1, y2, y3, like this. If x is a scalar, then only x I'm writing. Okay, I mean there is no component or something, right? Now similarly, if let's suppose y is a vector, x is also a vector, then you can write it as a matrix. Okay, if y is a vector, x is also a vector, which means every component of this will get differentiated with respect to every component of this. So see here that if this is just one scalar, then you will write like this, right? I mean, each of this y will get differentiated with x only. Okay. If x is also vector, then each of this y will not only get differentiated with just x1, it will also get differentiated with x2. It will also get differentiated with xm. Okay. So this each of this y I'm differentiating first. This is the differentiation with respect to x1 and so on, right? Okay. So let's just see this. Consider this as an expression. This is a vector or a scalar. This is ax. Ax is a vector, right? Ax is always a vector, which is a linear combination of columns of A. Now, what they are saying, differentiate this vector with respect to x. Okay. Differentiate this vector with respect to a vector, another vector x. Right. Okay. So let's just try doing it. So see here, this ax will be like this, right? I mean, this, let's suppose first row, first column A11, first row, second column will be A12, second row, first column will be A21, like this. So AX is something like this. And if you differentiate, this is a vector, X is also vector. Then this is with respect to X1, this is with respect to X2. I mean, each of the component of this vector with respect to X1, with respect to X2. Is this fine to everyone? Is this line fine to everyone? I hope this A into X is fine to everyone, but is this also line fine to everyone? Those who have not seen calculus lecture, just let me know. Each of the component of this with respect to X1, each of the component of this with respect to X2. Okay. So if you do this with respect to X1, each of the component, then it will be actually A11, A21, A12, A2, like that, right? So actually this AX, differentiation of AX with respect to X, is coming out to be A only, right? So we don't need to do again and again. You can just remember this, that differentiation of AX with respect to X will be just A. I mean, this is a common sense. I mean, AX with respect to X will be A. Okay. Is this fine to everyone? Can you just remember this directly, this result? Okay, let's see more example, and then I will actually come to this remember part or not. Okay. So can you tell me differentiation of A transpose X with respect to X? If differentiation of AX with respect to X is A, then what about A transpose X? You can just assume that to be B. It will be A transpose, right? So yes. So the answer is directly, I can say the answer from the previous, it directly follows from the previous result. It is A transpose, right? Directly A transpose X will be just A transpose. Okay. So actually we have just computed AX with respect to with okay, with respect to X is A. I think this is, we have not computed, but that's fine. Okay, we can do it. X transpose X we have computed. This is 2X transpose. Okay, we can also do it. If you do it, it will be A transpose. Okay, it will be A transpose. Anyway, let's not worry about it. So the I like, you can see the calculus lectures for more details. Okay, let's just even remove this. That's fine. Okay. So let's just see this question where I want to differentiate with respect to X. Okay, I mean, by default, I want to differentiate with respect to X. So I know that X transpose X, differentiation of X transpose X is what? If you remember, it was 2X transpose. Do you remember this? Differentiation of X transpose X, we did it. It was 2X transpose. Is this fine to everyone? Now you can apply something called a chain rule, which says that if differentiation of X transpose X was 2X transpose, then what is the differentiation of this? So it will be 2 into X transpose. It means currently the X is this, right? Into the differentiation of whatever you have assumed to be X. So it will be the differentiation of what? AX. Is this fine to everyone? Let me know. Right? Now, according to our notation, differentiation of AX with respect to X is just A. Right? So basically, I'm just using these two formulas directly. And I'm also using the chain rule to compute this. Okay. So I'm using these two and I plus the chain rule. So the differentiation of AX is actually A. So finally, this will follow to, you can take, this is transpose. Is this fine to everyone? Okay. Now let's do more question. Just one last question for our detour, and then we will come to whatever we want to do, right? Okay. So let's just do this question. Now, suppose I want to differentiate this fx with respect to x. Then let's just assume this whole quantity as an x, in the sense this is x transpose x. So if it is x transpose x, then it will be 2 into x transpose, right? See, do you remember that if it is X transpose X only, then it is 2 into X transpose. Okay. So 2 into AX minus B transpose into the differentiation of whatever you assume that to be X. Right. Now, what is this quantity? Differentiation of B, differentiation of B with respect to X is anyway 0. Differentiation of AX is, I think, A, right? So this is 2 into X transpose A transpose minus B transpose into A. Is this fine to everyone? Let me know. Okay. Okay. So it will be, you can say it follows X transpose A transpose A minus B transpose A. Okay. Just a second. Let me just check. Is everything correct or there is something we have missed? Yeah, 2 is fine. Okay. Okay. So I hope that is fine, right? Great. So this is how you can differentiate. So this was just end of detour that I wanted to just quick have a quick check. Okay. Now you can just revise these things. Don't worry, it will get in the flow. You can just revise this. Okay. It's not a much of the problem. You can just remember this and the chain rule. Okay. So now we have just found out that the quantity is 2 into X transpose A transpose A, 2 into X transpose A transpose A minus B transpose A, right? And to minimize, I want to make it a 0. Is this fine to everyone? To minimize, I want to make this a 0. Okay. Okay. So actually, I mean, as I told you that some people also write it as in transpose form. I mean, whatever result you are getting, some people also write this, not just this, they also write in the transpose form. I mean, that's fine. So can you tell me if you, let's suppose if you choose to write this in transpose form, so maybe, okay. I mean, you can see since anyway this is 0, you can take the transpose both sides, it won't matter. But let's suppose if someone is writing in the transfer form, okay. So what will the transpose of this? You can take 2 X transpose A transpose common minus B transpose into A. Okay, the transpose of this will be A transpose into the transpose of this, isn't it? The transpose of this will be AX minus B. Is this fine to everyone? I mean the whole transpose of this. So whatever we have got, I'm just transposing it. Okay, instead of column vector, I'm writing it as row vector or something like that. Actually, as I told you, it is just मतलब don't be too stubborn कि नहीं ऐसा ही transpose नहीं लिखना है या transpose लिखना है. मतलब ये थोड़े mathematical convenience के लिए whatever is needed we will do it. Okay, so for our mathematical convenience whatever is needed. So which means like if we are finding कि this looks like little, let's suppose clumsy or not very much obvious. Actually this has AX minus B. It is a nice form. So just do transpose. I mean, don't be too worry about it. Okay. And also in machine learning, it won't be coming again and again. Just in one or two times we will be seeing this, and don't worry about the transpose and this. Okay. So don't take too much of the tension ki why I'm doing transpose or something like this. It is just because I told you that you want to keep it as a row vector or the column vector or like that. Okay. So the layouts and these things are actually, to be honest, I have also Googled it. I have also searched it, but there is not a single place where it has a descriptive, answer in just a single place. So basically, people are using this here and there. So actually, the screenshot I have taken, they've used the transpose version, right? See, like if you remember, then we have got something like this, right? What we have got was like this, but in this screenshot, they are using the transpose version. So that's why I'm just telling. Okay. So here, now you can see, this is what we have got. They're having just a transpose of this, right? So that's fine. Is this okay to everyone? That the gradient is this? Let me know. So basically what you're doing, this is, if this is x transpose x, then it will be 2x into whatever you have assumed to be x, right? 2x into sorry, 2x transpose, 2 into x transpose, so what into whatever you have assumed to be x, and then you can take one more time transpose. Okay, that's fine. You can take one more time transpose, right? Okay. So let me know if that is fine to everyone. So actually in chain rule, I have actually observed that whenever we are applying the chain rule, people have actually done it. Matlab, after the chain rule ends, they put the whole transpose also. Okay. In chain rule, people have actually done it. So anyway, the gradient is this. Okay. The gradient is this. The final gradient is this. Now, now what we want to do, we want to make this gradient as zero and we want to find out the x. That was our aim, right? We want to make this gradient as zero and then we want to find out the x. See, we have started with the notation. Basically, don't worry about this two. This is L2 norm, but actually, let's not worry about it. So basically, we have started with the notation that we want to minimize. We want to minimize this error, right? This error. So this was same as ax. I mean, this y cap was same as ax, and then y, I was saying it is just b. Okay. So we want to minimize this. Now, in order to minimize, okay, even if I don't worry about the bicep and y, if I just give you the general optimization problem, okay, even if you forget that context that from where we have started, if I just say, okay, just a starting point, I'm just saying the starting point is this. Okay, let's suppose this is a starting point. Okay, I mean you don't know anything before it, you don't know anything after it. This is just a starting point. You take the gradient, and if I ask you that if you do it at zero, then what will you get it? Let's just see. Okay. If you make this gradient at zero, then what you will get? You will be getting A transpose into AX minus B equal to zero. I mean, this two is actually useless, which is same as, A transpose AX equal to A transpose B, right? A transpose AX equal to A transpose B. So basically, the initial motivation was actually, we will make it very clear when we start the projection and all in tomorrow's lecture, but today I'm just telling you, this was the initial motivation to solve, right? So we wanted to solve for x equal to b. Okay, we wanted to find the coefficient such that it gives you your ground truth, or your b or your y. We were interested in this, but it might be the case that it is not solvable. I mean, the points are not collinear. So we wanted to solve this, but instead of solving this, right, we are actually solving, right? I mean, we are finding out x here, okay? Finding x here. Basically, grad zero or gradient zero actually means finding the x using this equation. Is this fine to everyone? We wanted to solve ax equal to b, but instead of finding ax equal to b, we are solving for A transpose ax equal to A transpose b. Suppose A inverse exists. Suppose A inverse exists. In that case, A transpose inverse will also exist. So you can multiply by the A transpose inverse. So if A inverse exists, okay, if A inverse exists, then this equation, this will get just vanish. This will just vanish. This equation is nothing but Ax equal to B. If A inverse exists, which means if you can solve this, if you can, if this Ax equal to B is solvable, it means if A inverse exists, then whatever you are solving will actually trim down to Ax equal to B. So basically this is same as Ax equal to B only if A inverse exists. Anyway, we will talk about this more later on. Okay. So so what I'm saying here is that you wanted to solve above, but instead of solving above, we are solving this. Is this okay to everyone? Or in other words, in terms of the optimization, you can say that you want to minimize this error, right? I mean, this is the error that you want to minimize. So what you end up doing it, you end up finding the x which is a solution of this. I mean, you wanted to find x, so the x which solve this is your answer, isn't it? X which solve this is your answer. Is this okay to everyone? Okay. Okay, so let's just quickly see one example. Actually, this is called normal form. Okay, this is, I mean, this equation that we have just seen actually called normal form. Anyway, so let's just see this example. Let's suppose they say that find the equation of least square line for this data. Quickly tell me what is A. Your A will be basically this is your B, I think, right? Okay, A is just very small. 1 2 4 5 1 1 1 1. What is your B? 3 2 1 1. What is your X? Tell me. This will be little interesting. Can anyone tell me? Is this correct? C0, C1, is this correct? No, actually C0, C1 will be little wrong because C0 is not a coefficient of data. C0 is a without coefficient term. So C1, C0 is the correct way of writing X, right? C1, C0. Okay. So basically you have your A, X and B. Now what you want to solve, okay. See, you can directly solve for the normal equation, but ideally what we want to solve, right? And find X, right? But we can't solve it. In most of the time, we can't solve it. We will talk more about it. So instead of that, what we are doing, we are basically, I mean, if you want, you can go with the long process. You are minimizing with respect to X, right? So the long process is that if you want to have this, so grad of L will be something like that, and then it will be, I think, 2A transpose. Okay, this will be grad of L, and you want to solve for grad of L equal to 0. Is this fine to everyone? Let me know. Okay, so basically you have made your loss function, and then you are taking the grad. Ultimately it is coming like this, right? I mean, we have done this, so I'm not doing it again and again. Even you can bypass writing this. You can directly say that you are basically, we want to solve for X in this equation, right? We want to solve for X in this equation. So actually we wanted to solve for this, but we are actually solving, right? We ended up solving, or we are solving for this X. Is this fine to everyone? Why we are solving this? Because we have found out our loss, and we have taken the gradient, and then we made it to be 0, and then finally after doing all of this process, it is like this. Let me know if that is fine to everyone. Sorry, I think I made a mistake. This is A transpose B. Okay. So you don't need to, yes, this is a cheat way of saying that multiply A transpose. But why this multiplication makes sense and how we are coming up with this? Because of this loss function. Okay. We took the gradient, we made the loss function, we took the gradient, we evaluated to 0, and finally we are coming up with this, right? Okay. So you can solve X for this. So basically, if you solve it, okay, they're writing C0 first, and then that's why the reason they're writing this once first. Is this okay to everyone? It is up to you how you are making this A and X. Okay. So if you're confused that why this ones are first, because of C0, they're writing the first. Okay. I mean, that's fine. If you want to be very consistent, then you can write C0 first. I mean, consistent like that, okay, C0 should be first. Then you can make C0 first. That's fine. So A transpose A will be this. A transpose B will be this. So basically, you want to solve for this system of linear equation. Okay. So for example, I'm not doing the calculation, but ultimately they are saying that A transpose A, if you do it, then will come out to be like this. A transpose B, if you do it, it will come out to be like this. So basically, you can say that 412, 1246, C0, C1 equal to 716. You want to solve for C0 and C1. Now, you might be having one doubt. Do you have one doubt? Okay. You might be having one doubt, which is that earlier whatever was A into X equal to B, that was also system of linear equation. This is also system of linear equation. Why we are saying that we can solve for this, and why the earlier one was not solvable? You getting my point? So earlier also something Ax equal to B, right? Instead of A, I'm writing A transpose A. Instead of B, I'm writing another vector which is A transpose B. Okay. I'm saying that if this is not solvable, that's okay. But instead of this A transpose A into X equal to A transpose B, A transpose B, yeah, this is solvable. I mean, see, at the end of the day, this is also A, I mean, some matrix into X and equal to some vector, right? It is also Bx equal to C, right? I mean, some matrix B X into this whole thing, let's suppose C. So at the end of the day, this is also system of linear equation. That was also system of linear equation. But I said like, this is not solvable. If this is not, I mean, actually don't need to worry whether this is solvable or not. You can directly solve for this. Okay. If this is solvable, then you will be getting the same X. Okay. The same X will be shared. If the above one is solvable, here also you will be getting the same X. But if this is not solvable, then also I'm saying you can solve for this. Why that is the case? Actually, I have to talk about in detail. This will come in tomorrow's lecture, that why we are able to solve this. Okay. We will be able to solve this always. This particular thing on a like loosely speaking, this we will be able to solve this always. Okay. So we will talk about this later on, but is the process clear to everyone that how to find out the best fit line, in the sense that how to find this C0, C1, these coefficient? Just find out your A, or find out your X, find out your B, right? Like this, like this. Just gather your A, gather your X, gather your B, calculate A transpose A, calculate A transpose B, make a new system of linear equation and solve for it. Okay. So finally, it is coming like that C naught is basically 13 by 4 and C1 is minus 1 by 2. Okay. So let's see this question. Describe all least square solutions. So actually, the least square solution, or the solution of this, like solution of this, is called least square solution. Okay. Need not to be unique. It is solvable. It is consistent. But I haven't said that, okay, it has to be unique. in this case, this x seems to be unique. I mean, in this particular case, but here we will talk about it later on. I mean, tomorrow lecture. In this case, like this is the example where this x is actually not unique. Okay, so it is possible that x is not unique. So you will be having A transpose A, you will be having A transpose B. You will be making a new system of linear equation using this A transpose A and A transpose B. And then it is possible that you may be having infinite number of solutions. That's fine. You can just pick one of them. I mean, if you say that, okay, what is the best line that is fitting, this line is also fitting, and any multiple of this, okay, I mean the parallel lines, the overlapping lines are also fitting. So that's fine. You can if there are multiple solutions, all are equally good. Okay, the multiple solutions all are equally good. So you can pick one of them. For example, you can pick x3 to be 0, and then you can pick one of the solution. It's fine. So have you understood that how to find out, okay, how to solve ax equal to b, even if not solvable? So basically, instead of solve, I should be saying approximate, right? Or how to find the best x such that it is, or maybe in other words, how to find best x such that it is as close as possible to ax is. So what are the steps? Let's just quickly write down the steps. So you don't know what is the x, right? So you will be finding the x such that your distance between ax and b, right, should be minimized, right? So this is, you can say, is distance between a and b, ax and b, right? It should be minimized. In other words, you want to find out the minimum of ax minus b transpose into ax minus b. And in order to find out the minimum of this, such that I mean, with respect to x, we have found out the gradient, which was coming out to be 2 into a transpose ax minus b. Okay, the gradient was coming out to be like this, and then we said let's just make it to be 0. And if you make this gradient to be 0, you will be getting something like this. The cheat way of achieving this particular equation, which is also called as normal equation. Okay, what is the cheat way? You just multiply a transpose both sides. We will talk about this normal equation, these things later on. But if you minimize this loss, you will be getting this a transpose ax equal to a transpose b. Okay, but there is one more way of coming up with the same normal equation by something called as projection. Okay, so we will talk about this projection matrix later on in the tomorrow's lecture. So another perspective of this least square solution is using linear algebra, right? So we will be seeing the projection. Okay, and using the projection also without any gradient, without anything, right? We will not be even differentiating just a single quantity x square. Also we will be just getting the exact same equation just in just one line. I mean, here also it is just one line. I mean, lx and this grad, and then this is just like that. So also using the linear algebra, we will be getting the same exact same equation. Okay, so it is another way of looking at the same thing using the linear algebra. Okay, so we will talk about this tomorrow. So today we have talked about an optimization viewpoint of finding the best line. Tomorrow we will talk about a linear algebra point of view or viewpoint to find the best fit line. Okay, so ultimately we want to find out the best fit line. Now we have taken the gradient, we have found out the best fit line, but we can find out the best fit line using the linear algebra also, without even differentiating x square, without even differentiating a scalar x square. Okay, just using a single matrix. Okay, so how to do it? Just using the projection. Cool. So we will talk about the linear algebra perspective of the same thing, exact same thing tomorrow. Okay. And also, I will be just having 10 to 15 minutes of quick detour to the orthogonal projection so that we can set up the base. Okay. So tomorrow we will be actually coming up with the same thing and not be touching anything about the calculus, and the same equation we will be having. Okay. So thank you everyone. That is all for today. Okay. So this is basically the setup for your linear regression and for machine learning. Let's just have tomorrow class also, and after that I will introduce more. Okay, about the machine learning, in the sense what type of learning algorithm we have and so on. Okay. Thank you everyone. Take care. Bye bye. Yeah. Thank you, Akshay. So Akshay is saying that I don't know how 2 hours got completed. Thank you so much. So let me just uh, take the screenshot of your message. Tomorrow, yeah, tomorrow same time. Tomorrow there will be class at the same time. Okay. So thank you everyone. Take care. Bye bye.